A machine is tasked with predicting the future. It scans two individuals, scores them identically, and separates them into different legal outcomes. In 2016, this scenario became the center of a national debate surrounding Compass, an algorithmic tool used by judges across the United States to assess whether defendants awaiting bail or sentencing were likely to reoffend. The creators of the algorithm defended the system as statistically fair. Their evidence showed that a specific high-risk score resulted in the same probability of reoffending regardless of the defendant's race. However, investigative journalists reached the opposite conclusion. When they examined defendants who did not commit future crimes, they found the machine flagged Black defendants as high risk at nearly twice the rate of white defendants. Both groups were using the same dataset, and both groups were mathematically correct. The Compass controversy reveals a structural conflict between mutually exclusive moral philosophies. Because these specific mathematical definitions of fairness cannot be satisfied simultaneously, the dispute over what makes an algorithm fair is a matter of philosophy, not technical error. Fairness often rests on the principle of treating like cases alike, but in the context of machine learning, the debate hinges on how we define those similarities. Highlighted dots show reoffending base rates, 50% in population A, 25% in B. To achieve predictive parity, selection boundaries capture a 70% ratio in both. Yet A's higher base rate traps more innocent dots as false positives, violating equalized odds. This demonstrates a mechanical reality. When you apply a classifier to populations with different base rates, you cannot achieve equal meaning in the score without creating unequal error rates on the ground. The Kleinberg-Choldakova theorem is a mathematical proof that universal fairness is an impossibility in predictive modeling. The only exception is a system with 100% accuracy. To satisfy every definition of fairness, the machine would have to predict the future without a single error. Since perfection is impossible, developers must choose which error to minimize. This hard-codes a specific moral stance on who bears the burden of the machine's inevitable mistakes. Bias does not only emerge from the math of the model, it is also a product of the data fed into it, beginning with measurement error. This flowchart illustrates the gap between a target variable, like actual crime, and the measured variable, arrest records. Heavy policing in certain neighborhoods widens this gap, causing the algorithm to learn policing patterns instead of actual behavior, which reproduces historical bias. Bias persists even when data collection is technically perfect. This occurs when an algorithm reflects flawlessly accurate data captured from an unjust world. For instance, a bank may use wealth and income data to predict loan repayment. The data points may be entirely accurate, but if a specific demographic has less wealth due to historical discrimination, the algorithm identifies the lingering shape of that injustice and uses it to deny new opportunities. By treating these accurate but skewed histories as neutral predictors, the model automates the past, carrying prior injustice into the future. Many developers argue their models are fair because they are colorblind, explicitly ignoring protected attributes like race, sex, or religion. This is an illusion. High-dimensional machine learning, which uses thousands of variables to identify patterns, is designed to find correlations. If you remove a node for race, the system simply identifies peripheral nodes, like a zip code, that carry the same predictive information. This is the proxy problem. Because algorithms can bypass legal prohibitions using neutral substitutes, we are forced to define which data points are morally impermissible. One approach uses statistical fit, where a variable is restricted simply because it correlates heavily with a protected group. Under this definition, an algorithm that downgrades applicants from specific women's colleges is using a proxy for sex. Though the college name is neutral, it acts as a filter for a protected demographic. A second definition focuses on information value. A neutral trait is a proxy if its predictive power derives entirely from correlation with a protected trait. In this view, the college name is only valuable to the machine because it signals that the applicant is a woman. There is also the explanatory concept. Here, a trait like a zip code is a proxy because the only reason it correlates with race is a history of housing discrimination and redlining. Finally, the legal intent definition asks if the proxy was used deliberately to discriminate. In Personnel Administrator of Massachusetts v. Feeney, the Supreme Court ruled that a hiring preference for veterans was not a proxy for sex. Though excluding most women, the court found the intent was rewarding veterans, not harming women. Without a clear definition of what constitutes a proxy, simple pattern recognition can nullify the legal and moral protections meant to prevent discrimination. These algorithmic realities were forced into the public light by researchers like Joy Buolamwini. Her work proved that commercial facial recognition systems frequently fail because the data used to train them lacks representative samples of darker-skinned faces. Researchers like Timnit Gebru further demonstrated that these failures are intersectional. Intersectionality is a framework for understanding how overlapping identities, like race and gender, create unique modes of discrimination. In AI, this results in the lowest accuracy rates for dark-skinned women. This unfairness extends beyond loans or bail. Safia Umoja Noble has shown how search engines reinforce societal oppression by delivering results that reflect harmful stereotypes or pornography when users search for marginalized groups. We are left with three insurmountable obstacles: the mathematical impossibility of universal fairness, the self-fulfilling nature of historical data, and the ease of finding proxies. There is no line of code that can resolve the tension between different definitions of justice. The demand for algorithmic fairness forces us to make our trade-offs explicit. We must now decide how to balance mathematical accuracy against historical restitution and the distribution of human harm.